right, well, let's start with your homework assignment. Okay, finally, that's one homework assignment. So this homework assignment is about division. So this is the guideline. You're going to write a program to do division using TTP or text toy processor. So from here on, I'm just abbreviating that to TTP. So your input is going to be register A and register B. You can assume register A has a dividend, 8-bit wide, unsigned. You can assume register B has the divisor, also 8-bit wide and unsigned. In other words, this entire program only deals with unsigned numbers. You may assume the divisor is non-zero, which means you do not have to check for division by 0, because I guarantee that when I test your program, the divisor is non-zero. Which also means the range of values for the divisor is 1 to 255. The range of value for the dividend can be from 0 to 255.
2 to the 7th. 2 to the 7th power minus 1. 2
to the power of 8 minus 1. Yeah. Yep. You're off by 1. All right. So that's the input. The expected output of your program is to store the remainder of the division in register A and to store the quotient in register C. Is that okay? Are there any questions about what I want your program to do? Okay. A single halt instruction should be placed at the very end of your code to stop execution, because I don't want to keep, I don't want to have to do a control T manually just to make sure I don't get past the end of your program. And you may utilize additional RAM area for variables if you need it. Okay. If you don't need it, don't use any additional RAM locations, but if you do, go ahead and use some. Efficiency is not used for grading. In other words, you can use a very slow method for division, and one such method is called successive subtraction method, which is basically how elementary school students do division. Okay, 16 divided by 7. Oh, okay, 16 is at least 7. Subtract 7 from 16, increment quotient by 1. So 16 minus 7 is 9, right? 9 is greater than or equal to 7 again. Add another 1 to the quotient. Subtract 7 from 9, you get 2. 2 is no longer greater than or equal to 7. So 2 becomes the remainder, and then your quotient is 2. Okay? I just spelled out the algorithm. Okay? So that's an easy way to do division, and you can use that, okay? It also handles division by 1. It's just very, very tedious when you're dealing with division by 1. 255 divided by 1. 255 is greater than or equal to 1. Subtract 1 from 255. Add 1 to the quotient. Now you have 254, right? 254 divided is greater than or equal to 1. Subtract 1 from 254. Add 1 to the quotient and keep going. It also works when you're dealing with 1 divided by 6. Okay? 1 divided by 6, 1 is not greater than or equal to 6. Stop. The dividend is in register A, so is the remainder. You're done. Woohoo! What about your quotient? Should be initialized to 0. So 1 divided by 6 has a quotient of 0. Yes, by initialization, right? It has a remainder of 1, which is dividend register to begin with. You're all set. So that method should work really well, okay? And even though it is inefficient, it will still be okay, because if you crank up the clock of Logisim to 4.1 kilohertz, it's not going to take that long. Okay, maybe a second at the most. Is that making any sense? Yep.
Can we set Logisim to, when we highlight a wire, to show us unsigned?
Yeah. That you cannot. Unfortunately, no, you cannot do that. Okay. So if you want the unsigned value, there's a way to look at the signed value and then just do a quick conversion to unsigned.
Okay. Just because it always, whenever you highlight a line, it always gives you the signed value after the bit pattern.
Yep. Yep. I don't think there's a switch to do it.
Okay.
But the source code is available, so if you want to add that option, you can always do that. You just have to locate the right section of the code to change first. So that might be the hardest part, is to find out where to make that change.
Yeah.
The change itself is probably really minor.
Yeah. Okay.
Yep.
Thank you.
So any other questions related to this homework assignment? So I do have a suggested route here, which is not something that you have to take. You don't have to turn in any scratch work. You know, it's not. This is not a high school, you know, writing homework assignment. Okay, you don't have to turn in your ideas, your scratch work, and your editing, and all the kinds of stuff like that. Rough draft, yeah, all that stuff. So if I were you, I would write the code in plain C first, and I would be careful to use uint8_t whenever it is appropriate. In other words, I will limit the types that I use in the plain C code to make sure that I'm only dealing with 8-bit unsigned numbers. Okay, because you don't want to write an algorithm that works, but you need wider integers, and it's not going to work in the toy processor. So I would use uint8_t, which is a type def that you can use once you pound include standard integer.h. stdint.h is what you need to pound include. Okay. So once your structured C code works, then you want to flatten it so they can get rid of all the braces. You know, everything that is structured, you want to get rid of those. Then you want to run the program again to make sure that the flattened version continues to work. So at this point, you're still dealing with just regular C code, which means you can debug the program using GDB. You know, you can use the command line version. You can also use code blocks. Okay, you can do it in Linux, you can do it in Windows, do it on Mac OS X, whatever you want. Okay, so at this point, it is not dependent on the architecture at all. The next thing you also want to do is to continue to flatten the C code until each condition of a conditional branch only involves a single comparison. Because when it is boiling down to a single comparison, we can do compare in the toy processor, right? And we can also do conditional branches with the toy processor. So at that point, you're ready to translate into TTP or text toy processor assembly code. So I would defer the translation into actual assembly code until it is absolutely necessary to do that. Okay, so this way you can double check that the logic of the program is correct all the way down to the really, really flattened to your program of this code. Is that okay? What to turn in is really just the source code. The source code is going to be a single text file. The extension really doesn't matter. The name doesn't really matter because I'm going to save it, in a different name anyway. So, yep, go ahead.
Is that going to be like the comma separated values that we would load?
No, this would be the source code. So it would be the LDI, ST, LD, that sort of.
Okay, cool.
Yep. That's a good question. Any other questions related to the homework assignment?
In the assembly, every single statement has to be
on a line.
New line.
Yep. You can have lines that only have comments or empty. That's okay too. But each line can only contain up to one opcode.
Okay.
All right. So are there any questions? You got 1 week to work on this. I think it's reasonable. Okay. All right. So if there are no questions about this, we are going to move on and talk about other things, such as how do we deal with subroutines in assembly language. Yep.
We're going to go over
the absolute value thing?
value.
Oh, sure. Let's do that first. All right. So let's go ahead and take a look at the ungraded assignment, which is the absolute value thing. And I think we made certain assumptions. I think A contains the original value, and we want to use B to store the absolute value. Okay, so there we go. All right. So we'll right here. So this is the actual code. I just used comment here to basically say A contains the original value, B contains the absolute value of A. Okay, B will contain. Okay, there we go. All right. So the first thing you need to know is whether A is already non-negative or not. Because if A is already non-negative, there's nothing to do. Okay, just copy A to B, we're done. On the other hand, if A is negative, then we have to flip the sign of A and then put it into B. Okay. So the first thing we need to do is to say if A is less than 0, then we want to flip the sign. Otherwise, it's just a copy. B equals A, and over here B equals the negation of A, or the arithmetic negation. Now this one is kind of flexible. If it is more convenient to do the less than, that's fine. If it's more convenient to do the less than or equal to, that works too, right? Because 0, you can flip 0, or not flip 0. It's still 0. Okay, so are we doing okay so far with the equivalent C code at this point? Okay, everybody's convinced the C code is going to work. Okay, so what I'll do is I'm going to do this step by step. Okay, I'm commenting out everything just so that I don't lose the original C code, but then I can also sprinkle the assembly code throughout this code. Let's deal with the easiest portion first. We're just copying A to B, which is a single instruction called CPR, copy register. You have to remember the first register is the destination. This is where we store, and the second one is the source, which is providing the value. So that one is easy, not a problem. This one looks a little bit harder, but it's not too bad. Okay, so we'll deal with this later. And at this point, we want to deal with the condition. We want to see whether A is less than 0 or not. There's no way around doing a compare. Okay, you can do an and, AA, to set the flags, but I think I stole those instructions for something else. So you cannot do and AA, to test whether A. I kept some of those, but I got rid of most of those. So let's just say that we cannot do that. Okay, so we'll do it the more conventional way. So in this case, we'll say LDI B with 0, and A is already in A. So now the question is, we know that we have to do a compare, and hopefully we can just do one conditional branch here. Okay, change something I to the then to the else label. Okay, so the else label is going to be down here. So the question is, how do we compare and what do we put here so that we can just go straight to the else label? This spot can be an L, can be L. Now we know it has to be L or C. It cannot be C, it has to be L, because we're dealing with signed values, as opposed to your homework, which is dealing with unsigned values. Okay, but in this case, it is signed. It makes no sense to try to come up with an absolute value function when you're dealing with unsigned values, because everything is at least 0. Okay? All right. So what does it mean when we need to get to else? When we get to else, it means A is greater than 0 or greater than or equal to 0. Does that make any sense? Okay. So now we go back to here and we say, oh, okay, we can make the original thing if A is less than or equal to 0, we continue with the then branch, which means when A is greater than 0, then when A is less than or equal to 0, we go to the then branch. When A is greater than 0, we go to the else branch. Okay, so we'll say, put an L here. Now that we have locked down the JLI instruction to else, how should I be comparing? Should I do a CMP A comma B or B comma A to go to else?
A comma B.
A comma B? Now, if you use A comma B, that means if A is less than B, we go to else.
Oh, no.
That doesn't seem right to me. If 0 is less than A, we go to else. Because if 0 is less than A, that means A is already at least 0, which also means we don't need to do any calculation, we just copy it. Okay, let's check out what this means. Okay, jump if and only if B is less than A. but B is 0. That makes sense, right? Because if A is at least is greater than 0, if A is greater than 0, then there's no need to do the arithmetic negation. Okay, is that making any sense? I just want to make sure that everybody is convinced at this point.
What if A is 0 then?
If A is 0, we'll still flip it. It's not wrong. It's just a little bit wasteful of processing cycles, but it's not wrong. I mean, you get 0 back. Is that okay? All right. So now we are concentrating on this instruction here. Well, the good thing is B already has 0, because when you want to compute B equals negative A, it is the same thing as 0 minus A. Is that making any sense? But guess what? B already has 0. So that means this is a very convenient thing. We just say, oh, okay, just subtract A from B. We're done. And then we can jump to the else branch, JMPI to the, oh, not else, but we jump to the end of the conditional statement. And if it's going to be here, we'll put a halt instruction all the way to the end. So this way the program stops at the right time.
That's clever.
Well, it just turns out, to be very handy like that.
I like that.
All right. So, does it work? So we'll do a Control A, Control C, copy, and then we go to the drive. And I apologize for all those announcements, okay, update it. No, wait, don't update. Update again. No, don't update. Oh, here's a new version. Another new version. Yep, I seriously need revision control. All right, so we go to cisp310, go to processor, shared, and then processor, and then we open up the assembler. There we go. So once again, if you want to use the assembler, which you probably want to, okay, do you have to? No. If you write the source code and you're 100% convinced that your source code is correct without testing it, hey, you can always just turn in your source code as it is without testing it first. But I would assume most people want to test it, with the simulator first, which means you probably want to do a file and then make a copy of this particular file first. The other one does not work. If you say, what is the other one? Not move to, I don't have that option here because I signed in as the owner of the file already. But if you sign in as somebody else, there's one more option. In addition to make a copy, I think there's an option to link it to your Google account, but it doesn't say link. It says something else that is confusing. Yeah, add to your drive or something like that. That option does not create your own copy, which means you won't be able to paste your code into the source tab of the spreadsheet. So you have to use make a copy, because that means the created file is yours, and then you can make changes to it. Okay. All right. So we go to the source tab here. I was playing with some other programs earlier. So we just paste this new code. Whatever is after this code, we can just go ahead and select and delete. Okay. And then you want to make sure that there's no error in column B, because if I make a mistake, column B is going to complain. Then we go to RAM file, go to File, Download As, comma separated, and we'll put it into the temp folder as before. We'll call this one ABS for absolute value. Then it's time to start up your simulator. And I'm going to start with the processor as well. So processor wdpc2.circuit. Now, because I haven't really used this one before, after I made changes to the ROM file, I'm going to update it first. Okay, so I will go back to the browser, go back to the class, go to announcement. I'm showing you guys how to get it too. So when you go to the announcement, it has, oh, I thought, yep, view announcement. And then I followed up a few times, okay? So I said change, then I mess up, okay again, change again. So use the latest one. And this one you can see the time is like, okay, really tech is awake at that time.
Have you ever read change logs for like mobile apps or anything? And you'll see like 4 updates in a row.
Oh, they all pop up at the same time?
Because like I didn't actually fix the error.
I see. So save link as. And then we'll put it in the temp folder too. There we go. And then we go here, just right click, and then we load image from the temp folder. All.rom is what we want. Click open. All right. So I'm just going to be careful and double check first. So I will go to edit content and make sure that 400 has something in it. Okay, that's good. I would also make sure that D0, D5, those are all, there's a particular pattern to it. So D0, D5, down here. Okay, so these are good. Okay, they're looking good at this point. Okay, so that's good. All right, that's cool. I'm just double checking, making sure that things are looking okay. Then we can click the reset button, and then this time we load the actual program into the RAM. And the program is also in the temp folder called abs.csv. Open that. Okay, so at this point it's not going to do anything that's interesting because the registers are all zeros, right? So we'll go to the register bank and say, okay, we want to test it with something that's more interesting. So how do you want to change the register? Let's try some negative values. Because the whole idea of taking the absolute value is you start with a negative value, and then B should have the absolute value version of that negative value. -2, okay. So -2 is FE in hexadecimal because it is 1111 1110. So that's a FE. So you can just punch in the code. I mean that works. All right. So once this is done, it's time to run the program. So we'll go click simulate, and because I've done this enough times, I can just type Control K. So I type Control K. The program has now stopped. Type Control K again, and we examine things in the register, and you can see register B now has 02. So the code seems to work. Okay. Because the absolute value of -2 is 2.
How'd you figure out -2 in X? How'd you figure out -2 in X?
Because FF is -1, and 1 less than -1 is -2. Or you can do a bitwise NOT and then +1 really quick too. So that works too. Yep. So are there any questions about this particular program? Seems to work. No questions? How many people did it? Well, at least put some time into it. Okay. Okay. But
I didn't do the testing, but I did the code running.
Oh, okay.
Yeah, I was trying to figure out the logic first.
Yeah, I did.
Yeah.
Okay.
I have way more. Yours is way more elegant than mine was.
That's okay. As long as it works. Okay. So you don't have to go for the most efficient solution in this class.
Right. The ALU operation. JMPI. It's jumping to a specific line. So
It's jumping to a specific location. You specify where it is supposed to jump to.
yeah, and you said label, and label is sitting at wherever it's sitting.
Right. So label is a convenience feature, because if you don't use labels, then you will actually have to count and then figure out the actual location.
Can you put it in hex?
You can put in not hex. You can only use decimal numbers. Yeah. When you punch in actual literal numbers, you can only use integers that are base 10, but unsigned.
Yeah.
All right, so getting back to this example, let me show you what I mean by that. So if you don't want to use labels, like this else label here, that means you have to figure out that this is taking up 2 bytes, 1 byte, 2 bytes, right? And you have to keep adding until you get to this point. Then you go back and fix up this number else, or whatever it is, with a number. So it's very tedious. You can do it, but it's just really tedious.
Change code in between those.
Then you have to recalculate by hand, yes. Whereas if you do it this way, the assembler calculates it for you. Yep. Yep. So it's a convenience feature, but it's really handy to be able to use labels. All right. So are there any questions about this code? I managed to fit the entire program on screen at this point, which is nice. Any questions about the program itself or the workflow where I write the program inside a notepad? You copy and paste the notepad content into the spreadsheet, and then you go to the RAM file tab of the spreadsheet, click File, Download As, and you can probably choose between comma separated or tab separated. I just use CSV in general, and then that becomes the file that you load into the RAM module in Logisim, and then you just run the program. So are we good so far? All right. Yep.
What we're turning into is the actual code, not the assembly code, right?
Not the assembly code. So what you're going to turn in is this code here. So it would use mnemonics, and you probably will find commenting useful. Unless you can track a lot of things in your mind, and this is this architecture that you feel comfortable with and familiar with already. Because otherwise, you probably want to use comments to kind of remind yourself, if I'm here, this is what I need to do, and this is how I do it. So this way, you leave kind of behind a trail of documentation for yourself.
And you're fine with the document using it to having those comments?
Oh yeah, that's perfectly okay. Yeah, yeah. Mm-hmm. In fact, I want to encourage you guys to put comments into your own program because that's just good practice to begin with.
You can go back to it and understand what's going on.
Exactly. Yep. Especially assembly language programming where the code is really kind of difficult to understand. So 1 week from the time you finish writing the program, you may not be able to recognize your own program anymore. Happens a lot to me. All right.
One more thing, jumps that jump depending on a flag only jump if the flag is set to 1.
That is correct. We don't have the negated version of that.
Yeah.
Yep. That's partially why it is called a RISC architecture, because you can always emulate the effect of the negated version by using an additional JMP instruction. All right. Are there any questions at this point about this program? Okay. If there are no questions, we're going to talk about subroutines. Okay, so we're going to jump into something that is interesting. And before we get into the assembly coding of the subroutine, I will first point out where to find the notes for that, because that's kind of important. So we'll go back to the modules. And these are all inside the assembly language programming module. And you can see that there's a new note here. I just typed it up this morning at about 5 a.m. My cats were kind of surprised that, hey, you're up already. Give us some food.
They wake you up themselves sometimes.
Oh, they usually wake me up by about 5 o'clock. But this morning I woke up at 4. And my mind was already thinking about 4:40 and also this class, and they're like, I need to type something, I need to do something. So I went outside, and the cats were like, it's a little bit early for breakfast, but hey, we don't mind. Give us some. Yeah. Yeah, but I cannot, unlike some people, where they just kind of leave dry food out, for cats to eat all day long. First of all, the bigger of my 2 cats has no self-control. You leave out any food, he will finish all of it, or try dying. Die trying to finish all the food. Yeah. And then 2, they cannot eat dry food. Okay, when they were kitties, we tried dry food on these 2 guys, and they didn't like it. I mean, they were having stomach issues. And then the big guy was having a bulged out stomach, because he was just not feeling well. So we had to switch to raw food diet. Okay, it's actually easier than most people think it is. You go to KP is the best place because they got really inexpensive drumsticks. KP is a Korean. Yeah, out of Rancho. So each pound of chicken leg or drumsticks is about 60 cents. Okay, so it's human grade. Okay, we're not talking about some scrap stuff in the butcher area. So it's actual drumstick that people can eat. So you take it, you put it into a grinder. You need a really good grinder for this. Okay, I tried the not so good grinders and kill the grinder. So you need a good grinder. You grind the entire thing: skin, bone, meat, everything. Okay. Yep. So so whatever comes out, it's just like ground meat, except it has got bones in it. You add some supplements. You add salt. You add fiber. You add vitamin A, vitamin E, vitamin B, salmon oil.
Sure, not hard at all.
Eggs, huh?
Not hard at all.
No. You just mix the whole thing and then you put it into the small containers. Stuff those into the freezer, and you just take one out of the freezer. Two, we keep two in the fridge so that one is thawing when the other one can be served.
I'm jealous of those cats. They sure look wow.
Yep. For some cats, apparently it takes a long time for the cat to switch from dry food to wet to raw food. For these two guys, it took 2 seconds. It's like, hey, you want to try? Okay, fine. The interesting part. This is the most surprising part. So the boach went away. They stopped drinking a lot of water. In fact, most of the time, I don't even see them drinking water at all, because the food itself has a lot of moisture. But what was really surprising was the poop does not stink anymore. Yeah, it's really strange. Okay, if you think about it, it's really, really strange, because when you think about dry food, it's like, okay, cannot be that bad, right? But then the cat poop is like, wow, they can be pooping at the other end of the house and I can smell it. And then these days I can walk over, to the cat litter area and go like, that looks like cat poop to me. But I cannot smell anything, like nothing, absolutely nothing. It's just shocking.
You see they have a pumpkin spice cat litter now?
Oh God.
What?
Not pumpkin spice.
Yes.
Tell me more.
What more do you need?
No, but I don't need any, scent covering, with my cat litter.
My cat doesn't bury his poop. He's an asshole. So it's like, he'll just cut and run, and I was like, dude, it fucking smells. Like, come on.
No, mine is worse. We'll sit in there for like a half hour.
Well,
scratching
you
it.
save
Mine
on
too.
food.
And then like all
Save
that
on,
scratching, you can't bury it.
I don't know, okay.
Expensive
So 60 cents per pound, okay? It takes about, 10 pounds is about 2 weeks worth of food for 2 cats, okay? This is for 2 cats. So each month, we would consume about 20 pounds of, chicken legs or drumsticks.
Plus
And so times, 60 cents each, so we're spending about $12 just on chicken legs. So the rest, they're not really that costly, because if you think about it, you buy a big, bottle of, a big container of vitamin E, that's going to last you like a few years. If you only use it on the cats.
Like powder, or is it?
Huh?
Is it powder or pills?
You mean the vitamin? That's just pill. That's for people. It's human grade, pills. So you just add, all the supplements and whatnot. Let's say you add $2 to it. So if I buy my chicken legs from KP, then it's only about $14 a month.
How much is the grinder though? The really good grinder you said?
The grinder is expensive.
Yeah.
Because you're talking about $400 for the grinder.
Yeah, well that has to be factored into it, right?
But once you exactly. So
You
if
can
you
also start making sausages for yourself, just like that
Yep.
Seinfeld episode.
Yep.
Or hamburgers. Make your own ground beef and make it.
Yep.
Really clean
Oh,
that grinder there.
and we do that too. You can choose any cut, buy any
Yeah.
meat and go like, okay, grind it up. And a good grinder, it doesn't even slow down when it grinds up the bones, But if you don't like that bone crushing sound, you might want to put on some headphones, because it really sounds like
That
crushing
seller-
bones. It's like that.
How's it to clean?
Huh?
How's it to clean after?
It's not too bad.
Dishwasher? Or?
Yeah, I just put it into the dishwasher. The only part that's hard to clean is the grate of the grinder, because sometimes you get ligaments and bones and whatnot getting stuck in it. So I use my stainless steel chopsticks.
Stainless steel chopsticks.
Stainless steel chopsticks. You never need to replace those ever.
And they
You
don't
have a
rust 'cause
little
they're stainless.
texture grip at the end.
Huh? Yep.
Yeah, those are the shit.
Yeah, those are really
I
great.
use those at home. I use those to eat like Cheetos and stuff. You don't get stuff on your fingers.
In a pinch, you can use those as weapons too.
Yeah, right?
That's
Yeah.
right there,
Same for the
Yeah,
eyes.
intruder.
In the
Okay,
kitchen,
can I
reach
at
for
least
a
go
knife
get my
or stainless steel
chopsticks?
chopsticks.
You go like, sure.
You ask for an audio.
You just have to aim for the temple, right? Just aim for the temple. It might work. Or eye socket.
Eye
That might work too.
Alright, back to coding.
Is it like
15 minutes?
Yeah, I think
Had
it's 15, yeah.
15 minutes.
All right. So in this particular case, we have a subroutine. Okay, we have subroutine F, which doesn't do a single thing. Okay, because the whole idea is to illustrate how do we call and how do we return. Okay, calling is easy. The calling part is easy because all we need to do is to go from here to here, and we have a JMPI instruction that is perfect for something like that. So continuing execution from the caller code into the called subroutine, easy peasy, because the subroutine has a name, has a label to go to. Hey, no problem. The problem is, what do you do when you are here, when you're at the end of the subroutine?
Jump
Then what are you gonna do?
You jump
Where-
back to after the.
But how do you know where to go back to?
Label it.
Yeah,
Well, even if you label it, you have two places now, right? The first time you call F, it has to go back to here. The second time you call F, it has to go back to here. So depending on where you make that call, the continuation after the subroutine is done is different. So there's no fixed point to go back to. Where you need to go back to need to be stored somewhere. Yep.
Does the jump need to have a literal, or can it have a variable with the location?
You can have a
Label.
register, okay? But you only got 4 registers, so you have to be careful with, oh, I'm just going to put it in the register because you only got 4 registers, okay? So that's your challenge. The challenge is, how do I know as a subroutine where to go back to when I'm done? So we have to kind of do a little digression to talk about the stack, okay? If you have not been exposed to the concept of a stack, it's okay, we can talk about it here. A stack is basically a last in, first out container. Okay, whatever you put in first, last is the first thing that you retrieve. Okay, a very infamous example of a LIFO or last in, first out or a stack is a U-Haul truck. Okay, pretty sure some of you or most of you have an experience of moving or helping somebody else to move. So let's just say that you're moving, and first thing is you're very concerned about, okay, I need to have the location where I'm going to and a map of that location so I know how to drive to that location. Of course, this is all before GPS and cell phone navigation and stuff like that, right? So that becomes a major concern of yours, and you go like, okay, this is important, and then you put it into the granny's nuke or granny's portion, the innermost portion of a U-Haul truck. Okay, and then you start to pack up the whole truck, and then you slam the tailgate, and then you hop onto the driver's seat, and then you remember, oh, where's the direction and also the address of where I'm supposed to go. That's the first thing that you put into the truck. So what do you have to do now to get back that instruction of where to go and how to get there?
Everything out.
Yep, you have to get everything out because it's last in, first out.
Can't
Which
just
also means
switch
the first.
destination. Oh, never mind.
Yep, you cannot because it's a stack.
Yeah.
Yep. Another container that really should not be last in, first out, but most people use it as a last in, first out, is your refrigerator. Especially if you have a freezer.
You push things to the back of it.
Yep. You buy new stuff, and where do you put your new stuff? Do you take all the old stuff out put the new stuff in all the way to the back of the refrigerator and then put everything back on, well, that would be ideal, right? You know, if but most people don't do that. So instead, what do we do?
Shove it up front.
Yep, exactly. So what's going on at the very back part of your refrigerator?
Moldy food.
Yep, you have a mowed garden at the back of your refrigerator.
Or like those drawers in the refrigerators nowadays, you know, it's at the bottom.
It helps. It helps.
It kind of helps.
Yeah. Yeah, it'll be ideal if a refrigerator has carousels. So
Some-
this way it's really last in, first out, like a buffer.
If it was just like one, like a bunch of shelves with one depth, like couldn't fit huge things.
The other way to solve the problem is to have your refrigerator to have two doors. One door to put things in and the other door to take things out of.
So there's a circle.
Refrigerated
No, it's naturally a circular buffer now.
And the sunglasses rack, just spin it around.
The carousel, yeah, that works too.
Oh, like the whole fridge, I mean.
Oh, the whole fridge.
Like spin it around, open it from the back, load it up, and then spin it around.
Automation.
Yep, but I'm thinking that you guys understand what is last in, first out now. Yep. Yes. Okay. So when we talk about last in, first out or a stack, if you have taken CISP 430, you're probably exposed to the concept of linked list and stuff like that in order to implement a stack. That's a lot of overhead and a lot of stuff to do. So in this class, we go simple. Okay. So the way we implement the stack in terms of data structure is just this. Okay, so I use a pound define, to define the size of the stack. Okay, you can use a const if you want to, and we declare a local variable. We declare a static, probably a global variable called stack, which is just an array of stack size. Okay, and each item on the stack is a byte, and then we also declare sp as a stack pointer. Okay, that's what sp stands for. Is stack pointer. It really is just a pointer to a byte. Okay, so that's the underlying data structure. And the way you want to remember a stack pointer is the stack pointer always points to the last thing that you put onto the stack. Okay?
So if you're putting stuff in a loop, you would look at, you'd point SP to the last thing you put in every time.
Well, SP is always pointing to the last thing that you put onto the stack.
Yeah. But initially you have to go through it.
Well, so the initialization of the stack pointer remains to be a question that will be answered later. Okay. So the way we use the stack is, instead of the more intuitive way of increasing, the more things you put onto the stack, the higher the stack pointer goes. Instead of using that, we kind of reverse it. So the stack pointer is originally pointing at the very end of the area reserved for the stack. Every time you allocate and we want to store something, we do this code. We decrement the stack pointer, and then we store whatever you want to whatever the stack pointer is pointing to. That's how we push or we store something on the stack. So is that okay so far with this code?
So up above where we did stack as stack size, which is 32.
Mm-hmm.
SP would originally be pointing at 32, like, wait, what?
Element 31.
Well, then we decrement it before we add something, so would it be 32 and then we decrement
Yep.
it to 31?
Yep, exactly.
Okay.
You're right. So we initialize the stack pointer to one past the last element of the stack.
Cool.
Because we make the assumption that the stack pointer is always pointing to the last thing that you push. So what happens when your stack is empty?
So there's nothing there, it's past it?
Yep,
Okay.
yep.
Just do pre-increment.
That's why we have to pre-increment, because the stack pointer is already pointing to something that you push last. So you have to move the stack pointer one byte lower before you store something to that location. Now, in this one, I think I understand your question. You're asking why are we doing post-decrement instead of pre-decrement?
Yeah,
It doesn't make a difference.
I mean, in the second line, can't you just do star, parentheses, minus, SP?
Yes, you can.
Yeah.
Yep, but I want to kind of separate it into two steps, because one, the intention of SP plus minus minus is to reserve the space, because you're moving the stack pointer and say that, okay, we are moving it down here, so you're moving the bookmark of which part of the stack is in use first. Then you take up that space and go like, okay, this is what we are going to store at that particular byte.
It's easier.
Yep, much easier. It's also easier to translate into assembly code.
That's a good point.
Yep, and to retrieve, using this scheme to put something onto the stack, to retrieve something is exactly the opposite. So when you compare this sequence of C statements compared to this particular sequence of C statements, they are the reverse of each other, not only in terms of direction of the assignment, increment, decrement, but also in terms of the order of things. This is the last thing that we do. This is the first thing that we do. In other words, the first thing we do is not to change the stack pointer, because the stack pointer is already pointed to the last thing that we push on the stack. Hey, we don't have to move it, we just retrieve it first. So you dereference the stack pointer and store that to whatever, usually X is a register, okay? So you retrieve whatever content you push on the stack, put it into a register or use it for whatever purpose, and then you increment the stack pointer. That moves the stack pointer back up again, which also means that now you have more space available on the stack. You're basically reclaiming space on the stack when you do a SP++ or ++SP, doesn't really matter one way or another. So as you said, this one can also be done, using a single expression, which is X equals the dereference in parentheses SP++, because you want to use the value of SP as it is before you increment.
So we're supposed to flatten, which causes us to separate. If there's two operations in one line, we separate into
Right.
two lines.
Yeah, and this is already separated into two lines that are easy to implement. Okay. Now, because of this particular method of using the stack, your stack pointer actually needs to be initialized like this. So getting back to the C code here, so when you say stack plus stack size, it really refers to the location of the byte that is immediately after the stack itself, which is exactly what we want. So are we doing okay so far with the C code? Yep.
Is that because lowercase stack is going to be just trying to find out what the word is?
It's pointing to the
amount of memory that takes up is going to be just one of whatever 32. I don't know if I'm wording that right.
Let me see if I can illustrate it using a spreadsheet. I can use a spreadsheet
Stack,
for a lot of things.
So lowercase stack, when you did stack plus stack size, that stack right there is memory-wise is just going to be 1. So it literally is just stack size plus one more of that like memory variable type basically.
Well, okay, let's take a look at this way. So let's say this cell is where stack is. This is the first byte of stack. So okay, we'll make it very clear. This is stack bracket 0. Okay. But you can also refer to this particular address as stack plus 0. It has an address of stack plus 0. Pointer arithmetics, exactly. So this is stack plus 1, and so on. And let's see. Do you think it's smart enough to? Oh, it does. Ooh, I'm impressed. Or as Vader would have said, impressive.
Most.
This answered my question, so I don't know if you wanted to keep
Yeah,
going.
I'll keep going.
Okay.
Okay, so the picture looks like this, but the stack, when you say the stack has 32 bytes, only this portion is really used. So if I were to highlight it with a light color, this portion, the highlighted portion, is the portion that you're allocated with. But when we initialize SP is pointing here.
So
Initially.
I was thinking of it like stack was you were adding the 32 like stack size or max or whatever, and then like size of stack is what I was
Right,
thinking.
size of stack is the 32.
That's kind of what I was thinking.
Yep.
So is 32 the number of it's being shifted over that many?
Oh, 32
addresses?
is just an example.
Yeah, but are you shifting over 32 bytes or 32 memory addresses?
It's 32 locations in
Okay.
RAM, but since the RAM that we use is byte addressable, so it's 32 bytes.
But so uint 8 is 1 byte.
Yes,
If
uint
it was
8 is a
uint
byte.
16, it would be 2 bytes.
Correct. But
you'd have
most
to do-
computer architectures are byte addressable, so your stack pointer
Oh.
will still be pointing to bytes. So until you have processors that are not byte addressable, but instead is 32-bit addressable, then each location is 32-bit wide, and then your stack pointer will be pointing to locations where each location is 4 bytes wide. But with most architectures, even the modern architectures, they're still quote-unquote byte addressable, which means each location contains a single byte, which is only 8-bit wide. Okay. So are we okay so far with this picture? This is all good, okay? So the next question now is, how do we do this in assembly? Okay. So to do this in assembly, oh, I didn't say here, which is good, okay. So to do this in assembly, what we're going to do is we have to first think about the initialization of the stack pointer, which is going to be a little bit of a problem. Because in assembly, you have to first allocate one register as the stack pointer. Okay, we only got 4 registers to begin with. So conventionally, we don't want to use A because A has another purpose. So I'm going to use register D as our stack pointer. Is that okay? It just has to be one of the registers. So I'm going to use register D as our stack pointer. The question is, how am I going to initialize it? This is how I do it. In other words, the stack is located all the way to the end of the available space in memory. Because all the other allocations, when you write code, when you use byte and so on, they're all allocating from location 0, location 1, location 2, and forward. So it is safe to use the end of the RAM location as your starting point of the stack. That will give you the most space available without having to do any calculations. Is that okay? But 0 doesn't look like a very big number to me. So why would I initialize the stack pointer to 0 when I really want it to be 1 byte past the end of all the addresses of locations? Because we have to subtract 1 first. What happens when you subtract 1 from 0? You get FF, okay? So when you interpret it as a unsigned value, what is FF? 255,
Yeah.
which is the largest value you can represent using 8 bits. So that's why this is how we initialize the stack pointer. So, okay.
Do you always have to be this clever with assembly?
Huh?
Do you always have to be this clever with assembly?
Well, you can also do this with other instructions, but I'll stick with this one. So now we want to basically push a value. Let's say push a constant, okay? We want to put a constant of 5 on the stack. Push, by the way, is just a term that refers to storing, okay? So we're trying to store a value of 5 on the stack, okay? So the way to do it, now remember, you might have a lot of code in between the initialization of the stack pointer and the code that you want to use to push a 5 on the stack. So you cannot really just say, oh, we know this location should be 255, because you have no idea how register D or the stack pointer is modified between this line of code and this line of code. So at this point, all you can say is to say, okay, I know register D is pointing to the last thing that I push on the stack, so what do we do? Well, fortunately, we have the C code available to refer to. So the first thing we need to do is to subtract 1 from the stack pointer, which is our register D. And using the introduced instructions, this is really kind of cumbersome because you have to put the 1 into A first, and then you say subtract A from D, like that. So it's really cumbersome, and it's really slow. So that's why I have a new instruction that you guys can use. It's called decrement. It makes it a little bit easier, right? I mean, it makes your program a little bit easier and easier to read. So decrement D.
But it doesn't exist in normal assembly.
It does.
It does.
Yeah, most processors support increment, decrement as individual instructions. It's also a lot faster because you don't have to go out to RAM to get something. Yep. All right, so we decrement D. So that takes care of. So I'm using comment here to indicate what this is doing. This is basically saying SP is SP minus 1. If you want to use that auto decrement or post or pre decrement, that's fine too. And then the next thing we do is to store the 5 onto the stack. Now this time we really don't have a way to get around it. So we put the 5 into register A, and then we do STD with A. So this way we are storing the constant of 5, which is now in register A, to wherever register D is pointing to, and register D is our stack pointer. Is that part okay?
Why are the parentheses around D?
Because that's the syntax that I specified.
Okay.
Yep. To emphasize that D is dereferenced.
Not the address.
D is the address, and then we are storing A to whatever that address is. We're storing A to the content corresponding to that address. So if you want to, so there are different ways to look at this instruction, std, A. You can also look at this as D driving the address bus of the RAM. RAM is selected, it is enabled, it is being written to. So D is driving the address bus, and then A is driving the data bus. And then you have the LD pin being low, you have the select pin being high, and then the next rising edge clock will store whatever register A has to the location that is indicated by D. Is that making any sense?
Onto the RAM.
Into RAM. So this is actually storing it's storing 5 to RAM, but it is using the last in, first out method to do it.
So this would be the same as A equals asterisk D.
The other way around.
D, asterisk D.
Asterisk D equals A. So this is the same thing as
Right.
Content.
it's doing this,
Yeah, okay.
because we are storing.
Perfect.
Okay. So what about popping? Okay, so when we say pop, it means we're retrieving something. So we want to pop stack value to, I don't know, let's say register B in this case. Okay, so let's see how we can do that. Well, the first part is easy. Remember, we are really reversing all of these operations, but not only in the sense of store and load, but also the actual sequencing of the instructions will be reversed as well. So this one starts with the LD, because D is already pointing to the last thing pushed on stack. So we want to load whatever D points to register B. In other words, this is what we're doing. B equals to star D, or D reference D. Then we can go back and go like, okay, since it's already used, I don't need that location anymore. So you can now increment D, which is the same thing as plus plus SP, or SP plus plus, so that we are deallocating that byte that is now utilized already. Is that okay?
So all the handling of the stack is done manually.
Yes. Now, with a CISC architecture, they have push and pop instructions, where the push instruction is a combination of all of these instructions, and then the pop instruction is a combination of these two instructions. But the RISC architecture, is RISC because we want to reduce the number of instructions, and that's why they're separated like this.
That's why Microsoft uses C++. It's CISC, or can't be CISC.
No, not really, because once you have a compiler, you can have a really bare bone RISC processor. The compiler just has to crank out a little more code, so it's no big deal as far as C programmers are concerned. So we're doing okay so far with pushing, which is storing something on the stack, and popping, which is retrieving something from the stack. Is that good? Okay. So if this is good, then we can go back and talk about subroutines. Okay, because now we can say, how do we call a subroutine? To call a subroutine from the caller's perspective, this is what we do. So we'll take a look at these 5 lines here and try to understand what is actually being done here. the first line, line 1, is decrementing D, which is allocating 1 byte on the stack. We are preparing to store something on the stack. Is that okay? So line 1 is fine. Okay. Line 2 is really just saying, okay, we are going to put the value of this label, L1, which is a continuation point, to register C. Now you can put it into register A, B, or C. I just chose to use register C. Is that part okay? You can use any register other than D because D is now dedicated as our stack point. Is that good? Okay. The third instruction, line 3, is going to store C, register C, which now has a value of label L1, but not what is at label L1, it's just the location L1 itself. It's going to store that onto the stack. So now we are saving the return address on the stack before we continue execution in the called subroutine. Is that okay? So you're preparing for the subroutine so that the subroutine knows where to go back to. So after lines 1, 2, and 3, after we have saved the return address, now we can safely transfer or continue execution in the subroutine, and in this case the subroutine is F. Is that okay? All right. What about returning then? So in order to return, which is at the end of function F, these 3 are the instructions that we perform. So what we do is we first go to locate the location pointed to by the stack pointer. We say retrieve that byte to register A. Okay, we'll use register A later on. Then we increment the stack pointer D, because that byte is no longer, it doesn't need to be stored on the stack anymore, so we are deallocating that byte from the stack. And then we use a JMPA, which is not a JMPI. So this one is really just copying register A to the program counter, so that the next instruction after line 3 is whatever we store earlier on the stack. Is that okay? Okay, we can also look at it this way. Lines 1, 2, and 3 from the caller perspective is pushing the return address. It's storing the return address on the stack. Lines 1, 2 of the return code is retrieving the return address from the stack. And the line 3 of the return code is just utilizing that code, utilizing that address and saying, okay, let's continue execution over there. Yep, go
I
ahead.
think I missed a part. So this is going to be like at the bottom of the stack?
This
Or is it?
is at the end of F, at the end of the subroutine.
So F is the subroutine.
Hmm?
Then I was gonna say, so F is the subroutine.
F is a subroutine.
Yeah. And then
So those 3 lines at the end of
Yep, those 3 lines are at the
the-
end of a
the
subroutine.
return statement.
Yep, they are basically doing the return statement, or the implicit return statement if your function does not return a value.
and then at the end of the subroutine F, there's gonna be a jump to L1, basically, or
No, it's not jumping to L1, it's jumping to A, whatever register A has. Okay, so let's go ahead and put this program together, and then we'll figure out how it works. Okay. So we'll go ahead and make another program, make a new one like this. Okay, so I'm just going to use this to initialize the stack. Okay, initialize the stack pointer. Okay. And what we understand as main is really the code here. Okay, so by the time we get to main, the stack pointer is already initialized. And we want to set it up to call F just like in the C code. So we'll do this thing here. We would allocate a byte on stack. Okay, allocate byte on stack. LDI A with return address 1. Okay, so there are multiple return addresses here because we have multiple calls to F in this case. Okay, return address 1, and then we'll do the ST instruction. Okay. Save return address 1 on stack. Then we can actually continue execution, JMPI to the subroutine F. Now, F can be defined later on. At this point, I'm not concerned about the label F. I'm going to put the return address 1 label over here. So this way, after I continue execution at label F or function F will do whatever it needs to do, right? At the very end of function F, it's going to have the return statement, and then the return instructions, I should say, the return instructions. The return instructions will somehow retrieve the return address 1 that is now stored on the stack, and then use it to continue execution at this label. What am I going to do at this label? Do the whole thing again. So I'm going to call it one more time, decrement D, LDIA, but this time with return address 2. So this is what allows a subroutine to return to a different place depending on where it is called. The continuation point is what is changed. So same thing, std with a, jmpi. Once again, we're calling F. We only got one subroutine, which is F. This is return address 2. And then at this point, main is done. So instead of exiting, we just halt. Okay, we don't have any actual way to exit the program per se. So now we have subroutine F. Okay, so subroutine F, you can do whatever you want, bunch of no-op instructions, whatever. Okay, when you're ready to say, okay, we're done here, then you have to use the 3 instructions that will implement the return statement in C. First one is LD. You're basically saying whatever is on top of the stack right now should be the return address. Okay, but if you mess up the stack pointer and it points to somewhere else, then you'll be using the wrong byte as a return address, which can be very bad. Okay. And then the next thing we do is we increment the stack pointer because that particular location is already used. We are done using it. So we better deallocate it so that it can be used later on for something else. Then we have a JMPA so that we are using the address that we popped from the stack earlier from the LD instruction. Now we use a jump instruction and say, hey, you want to continue execution where A is pointing to, because we are basically copying register A to the program counter. So whatever instruction is right after the JMPA instruction is whatever is in A. It's going back to the location.
So A is holding, if we called from the first call, JMPF, return address 1, JMPA would be going to.
So because this is eventually stored on the stack, this is what is going to be loaded back into A and utilized in the JMP instruction. Is that okay? All right, well, let's go ahead and give it a try. So.
But you don't have to halt the function because it just returns.
Yep, you don't want to halt the function itself because the function needs to go back to the caller.
So should there always be one halt in an assembly?
Yes.
And only one?
Well, when you're debugging, you might want to sprinkle halt somewhere else. But when your program is working correctly, then you probably only want to have one single halt in the code that is corresponding to main.
Yeah.
A return 0 at the end. Like a return 0 at the end.
Yeah, it's like return 0 or exit 1 or something like that.
Curly bracket.
All right, so let's go ahead and see if this works. Control C, Control A, Control C to copy the whole thing. Go to the assembler page, go to the source tab, and then we just paste the whole thing in, okay? Make sure that we don't have any errors on this side. Go to RAM file, save or download as, here we go. And then we'll save this one as call return. Then we switch to Logic Sim. Control R resets the simulator, so I don't have to click the button. And then reload the RAM content from call return.csv. So now we have this program. Now this program is a little bit different from the other programs because it doesn't have a whole lot of side effects on the registers. So you really can't tell whether it is going through the code correctly or not. So we have to rely on tracing the whole thing using logging, the logging feature, which is basically tracing. So we want to trace a few things. The program counter is definitely important because the program counter itself tells us, where did we go to execute instructions. So that's really important. Other things that are important would be the stack pointer itself. So the stack pointer is register D. This is register D. We want to track that. Anything else that you want to track? These two are the most important. We also want to track the content on the stack. So the content on the stack is a part of RAM. The RAM itself has 256 locations. We are not interested in most of them. Okay, we're only interested in location 255 to really, because it should never use location 254. It's going to reuse location 255 for the second call, because after the first call, that location is freed up already. So in the second call, it's going to reuse location 255 to store the return address known as RET-ADDR2. Yep.
That's what I was wondering about. So for this program, we really don't even need the stack. Really, we could just store the location in just a normal variable. Like we don't have to do it for this program at least. We don't. Really
Well, we don't have any variables. We only have registers.
Yeah, right in the registers.
Right. So what I'm trying to teach is the general strategy of any C program. In other words, underneath a regular C and C++ program, even for the Intel architecture, is really doing all of this stuff under the hood for all the function calls. Okay, it's just that with our architecture, it's all spelled out because it's a RISC architecture. For the Intel architecture, they have a call instruction to combine all of that stuff into one single instruction. In our case, we have to separate it into like 3 or 4 instructions. Yep, go ahead.
Basically, if we had subroutine and a subroutine, like subroutine that calls another one or something, the stack would be like address, 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 and then
Correct.
as we pop out of a subroutine back to the bigger scope, larger scoped one, we're popping back up
Yep.
the stack.
Yep.
That's cool.
So there's a stack of variables for every function. As long as you're still in the scope, there's a...
Well, the stack pointer is universal to the entire program.
Well, I mean, for every variable it's being put on the stack until it's out of scope. It's removed from the stack.
We'll deal with variables
Yeah,
later.
yeah.
Yep.
That's actually what I was going to ask, is in a real processor, how are variables dealt with? Because I'm assuming it's not a one-to-one relationship between that and the register.
Variables are not mentioned in this particular sample program, because what we're trying to do is to emulate the program, the C program that is already listed at the beginning of this entire thing. So this is what we're trying to emulate using the toy processor. So in this entire program, we do not have a single variable, local or global. So when we deal with local variables, it's going to be a little bit different. So I have to go over how call and return works first, how the stack works, because all your local variables and parameters are actually on the stack as well. But we can only stack up those additional concepts after we are done with the basic calling and returning. So that's basically what we are doing here. Right, so we're tracking location 255, and just for the heck of it, we can also track location 254, which should never be accessed, okay? Should never be read, should never be written to. So this is all we're gonna track. And then we go back to the simulator, we do a Control K to start clocking, and it's all done. Okay, you can see it's really fast. Control K again, then we go back to logging, we go to table, and then now we can try to analyze what happened. And by the way, you can also send this to a file, which makes it kind of easier to read. If you send this to a file, you can archive that. You can also print it out. You can do all kinds of stuff to analyze it. So let's figure out what is going on here. This is the program counter. The program counter is always telling you which instruction is getting executed. So in this case, the effect of executing,
No, go ahead.
well, it's initializing register D to 0, but it's 0 to begin with, and that's why the effect is not known, cannot be seen. This is the decrement. Okay, so by location 3, we have a decrement, and the end result of decrementing is register D is now FF, or 255. And then we store the return address at about this point, and that's why we can see location 255 is changed to 8, basically. Okay, so the first question is 8 really the right return address? Well, we can check that. we can now go back to the assembler page. And this time we have to go to the Assemble tab. With the Assemble tab, it has the original program here, but it also has the actual code generated here. Column V, by the way, is the locations. This is location 8. So it saved the right return address on the stack. Is that okay? And then switching back to the log. So after it saved location 8 on the stack, which is our return address, it continues execution over at the subroutine. So where did it transfer control to the subroutine? We're looking for a discontinuation of the addresses. So we got 5, 6, 7, and then we jumped all the way to 1111, which is location F or 15. So now this is another point where you need to check. It's like, did we go to the right subroutine? Is that the right jump, to the right destination? So we go back to the assembler and we locate the definition of F, and that turns out to be location 15. So we did go to the right location. The program counter indicated that we jumped to the right location. Okay, now we continue to read at location F. Okay, it goes to location 10 in hexadecimal and so on. And at some point we should see, I forgot to put register A in the watch list because that's kind of important when we jump back. Okay, but we can see where we stay in the subroutine and where we jump back to the caller. This is in the subroutine, right? Okay, from here, this is in the subroutine, and go so on. This is back to the caller. This is back to the caller because 1000 is location 8, which according to the assemble page, location 8 is exactly where return address 1 is located, and that's location 8. So from location 8, it continues execution to location 9, location 10, location 11, location 12, location 13, and then it jumped again. It jumped all the way back to location 15 because this is our second call. So the trick now is, does it know where to go back to? Well, where it's supposed to go back to is stored on the stack. So 1110 is supposed to be the return address, which is corresponding to the label of RETADDR2, return address 2. Is that really the case? Return address 2 has a quantity of 14, and it is represented as 1110 over here, and that is correct. So this is how you can kind of track down a program and figure out, okay, did we make the call correctly? Did we return from the call correctly? Now, if I also keep track of the other register, that is used for jumping, then it'll be even more clear how we got back to the caller. So are there any questions about this particular way of calling and returning? Well, I got one question for you guys, okay? Conceptual question. Can we deal with recursion using this particular way of calling and returning? Yep, we can.
But you need a bunch of registers.
Nope. We don't need a bunch of registers because it is the stack that is storing the return addresses. The registers are really just saying, hey, look here for the return address. Oh, wait, look here now. So that's why, with this particular way, we can now deal with recursion. The trick with recursion is not to look at things from the perspective of there's one blah, blah, blah per function. Because when we think about function, okay, let me go back to the listing first. When we think about what a function is, this is what we think about as a function. It is a static definition of a function. But a lot of things that we do in runtime is on a per invocation basis. What is an invocation? A call. This is an invocation. After it ends, we have a second invocation. When you have recursion, what is happening is from one invocation of a subroutine, you can create a second invocation of the same subroutine. Okay? The return address is not allocated on a per function definition basis. It is allocated on a per function invocation basis. So each invocation has its own return address. And that's why recursion is okay. You can go deep, and each level knows exactly how to get back to the previous level. Are we doing okay so far with this? Because in terms of instructions, we are not introducing a whole lot of new instructions, but in terms of concept, we are making some really new, kind of, you first, and then you, and then you. Go ahead.
Whenever we do this, though, we're taking up 2 registers out of the 4 available to us. So whenever we do anything, we only have 2 registers to work with.
Well, we're only using one as a dedicated register.
Yeah.
So the other register is just kind of floating around. So we technically only use up 1, and then we have 3 available for other things.
But the like load up, like we're using register A to
Mhm.
put the return address 1. So like we couldn't use register A to store anything that we need to keep, right? Like,
But only during that particular block of code.
yeah. But
But
I'm saying if we
you-
needed 3 registers to store 3 different values, we'd be kind of screwed.
Yeah, you will have to swap in and out. You
Mhm.
will start to use local variables in that case.
Oh, yeah, okay.
So we'll talk about local variables too.
Okay.
So what happens to the data with the last function? Because while it's in the scope, the data is still saved, right?
Say that one more time.
So when you on the register.
Yeah,
Okay,
so
no.
it's not where you don't, it'll always be there even if you start backing out of the function.
There's no scope issue, with assembly language
Right.
programming. So because everything is inside the same source file, and the registers are universal to all subroutines. There's no such thing as local to a particular subroutine anymore.
Oh, you went okay.
It's all in the stack.
So that even this is flattened out, basically, right?
Oh, this is completely flattened out. There's no scope issues whatsoever. Yep.
Gotcha.
You go ahead.
Two questions. So, you showed us the absolute value assembly, and then you showed us this. Do we have enough knowledge to be able to, with this stuff we just learned, we can actually make a function that does the absolute value? We could call it. and return it?
Not yet.
Not yet? Yeah.
Not yet. Because in order to do the absolute function thing, okay, so this is how the
You have to pass
Okay.
something on.
yeah, so you have to pass something and you have to be able to return a value, which we have not talked about yet. The next slide does talk about that. Let's see. I'm trying to find out whether I have it linked already here. Yep, returning a scalar is here, but not parameters. Okay, so we are still a little bit away from being able to call a subroutine, pass parameters to it, and then be able to take a return value out of it. But all of those will be done. In other words, even though the toy processor itself is very, very limited in terms of what you can do, but it has sufficient instructions to implement everything that you can do in C. So we're just looking at each one in this class and focus on that and go like, okay, so this is how we do local variables. This is how we pass parameters. This is how we get back to the parameters inside the subroutine. This is how we use local variables, and so on.
It's like cisp310 all over.
Yes, in a way it is.
When you showed us the logging and it showed the number, it enumerated each instruction. You mentioned before we can only have 300. We couldn't have a program that's 300, more than 300 lines of code and that's due to the number of instructions, isn't it?
Okay, there are 2 limits. One limit I can bypass just by making the assembler bigger.
Yeah.
The other problem has to do with you only got 256 locations in RAM,
Which
and
is
that is a
256.
much bigger limitation. To change that limitation, we'll also I have to change the width of the registers. Because you have to change the width of the address bus, so you have to change the width of the registers. So that's going to be a major undertaking to extend the architecture beyond that.
There's a max of 256 instructions or 255.
256, because it's location 0 to 255.
Right.
Right. So including comments and whatnot, you can only have up to 300 lines at this point, but that can be extended just by, copying these rows, further down.
Oh, does it put in, when you have a comment, does it count as a blank line?
It depends on where the comment is. So if you have comments like this, it's okay. If you have comments on an empty line like this, then it's just an empty line.
Oh, okay.
Yep.
You can't comment. We can comment in TTP, but can we comment in other syntax?
Yes, you can. The syntax is slightly different. With some, you start with a semicolon. With others, you start with a pound sign.
That would mess with me.
Yes, yeah. C programmers don't like that.
Yeah.
But I just use // because we're all used to // Yeah. All right. So this is the end of today's lecture. Please read the notes. At least you'll keep up with this section. I'll be posting some additional notes too. Between now and next Monday. And then I'll see you guys on next Monday, unless you go to the lab and we can do the homework over at the lab.
I feel like you understand this.
Yeah. Like, same here. I want to practice some more with it. Because, like, me messing